Okay, so here are the authors of RESIDE. Ryan Field is a research software engineer, Claudia, health, and Neil and Olivia are health economists, and I'm a clinical epidemiologist with a background in routine healthcare data. So RESIDE is an R package. It's available on CRAN, the code's on GitHub. There's our little hex there. And the principles of RESIDE are about communicating about data. In particular, communicating about data that's in some kind of secure environment, like a trial repository or a safe haven. And what we wanted to do was create something that was easy for safe havens, that it was transparently non-disclosive, not non-disclosive in the way that you might say that you have, let's say, you're a complex synthetic data algorithm. You may be confident that the probability of re-identifying someone is very low, but we wanted to make it blindingly obvious to the safe havens that the chances of re-identifying an individual of disclosure was very low. And we also wanted to make it easy for end users. It's a GPL3 license, and people are welcome to contribute. We've not got a contributor statement, but we will get that soon. So here is an overview of exactly how RESIDE works. So imagine that you have a safe haven. So for example, in Scotland, we have the Idris National Safe Haven. We've got a safe haven in NHS Greater Glasgow and Clyde, and so on. There are data in there about individuals that are difficult to access. It takes a lot of time. You have to sign data sharing agreements. You have to go through approval processes. It can take months, years to get hold of data. So what RESIDE does is it takes that data, it generates some summary statistics in a single function. It exports those summary statistics to text files, which are human readable and machine readable and are clearly non-disclosive. And then those files can be inspected and then just simply emailed to a researcher. And that's the red arrow there breaking through the wall of the safe haven. And then the RESIDE also works on the other side. So the idea is then that the end user runs a single function called import marginal distributions, which reads those text files into R, and then they can synthesize data. And we can synthesize it in one of two ways. You can either assume independence, or you can assume correlations, maybe based on external data between the variables, and allows you to synthesize data. The purpose here is for end users to get a real understanding of the data that's held within the safe haven. I don't know what other people's experience of this is, but often with the best documentation in the world, with the best will in the world, it can be very hard to get a sense if the data really is fit for your purpose until you get hold of it. People tend to ask for lots of variables just in case they need them, which can slow down the approval process. So RESIDE is really a communication tool to try and deal with that. Okay, so first point, easy to run for safe havens. So obviously categorical variables are pretty straightforward to summarize those. You can just give the proportion in each category and have some kind of cutoff, but continuous variables are more difficult. Now, if you had the time and resource and you're able to plot the distribution of those continuous variables, you would probably want to fit some kind of parametric distribution to them. But we wanted to create something really easy for safe havens. So instead, we used ordered quartile normalization, which is a really simple method which just ranks the data points and then assigns those to a cumulative distribution function and then converts that back into a standard normal distribution. And here's an example of it. So imagine we had a t distribution with 3 degrees of freedom, and here's a QQ plot for the normal distribution, and you can see that it's not normally distributed. And then all you need to do to convert it is there's an R package best normalize. It does the ordered quantile normalization, and that conversion, it gives you the original data, which is the $x here, and it gives you the transformed data here, which follows a standard normal distribution. And here's the plot of it here. So now it's as long as there are no ties, it's absolutely guaranteed to be the standard normal distribution. So the nice thing is then is that you can convert back and forward between the original and the transformed variables using a lookup table with linear interpolation. So here's a plot. On the x-axis here, we've got the original variable, and on the y-axis, we've got the transformed variable. Each of these points are data points in our table, and you can just look back and forward between them. However, safe havens are not going to want to give you 1,000 data points to summarize the distribution of a variable. So the way we deal with that is with something called the Raymer-Douglas-Pucher algorithm. I hope I'm pronouncing that right. So it comes from the world of cartography, and it's just designed to reduce the number of data points needed to represent a polygon. So again, it's non-parametric, and so we just run that on the data. There's a fast implementation of the Raymer-Douglas-Pucher algorithm in C or C++, I can't remember which, and that reduces the number of data points, decimation they call it. So here you can see we've got the original points in black and the lines between them, and then we have the decimated points as the blue squares. So you can see that in 1, 2, 3, 4, 5, 6, 7, 7 or 8 data points, we summarize an approximation of the relationship between the original variable and the variable transformed into the standard normal distribution. So that means that it's 7 data points. It means that the safe haven can summarize the distribution of a continuous variable using just 7 data points. And they can do so without needing to know the distribution and go to the trouble of finding out how it fits. Okay, so what does it look like if you are a safe haven? So you load up RESIDE. Here is just an example data set. We're using data from the International Stroke Trial because that's in the public domain. And all you do, just before I show you how to do the export, we're just showing you here that we just fit a model on the data. We're looking at the risk of stroke and the predictors being age, sex, systolic blood pressure at randomization, and the delay between, I think it's the delay between the stroke and thrombolysis, something like that, or stroke between stroke and randomization. Okay, so how do they use it? They just use this function here called get marginal distributions. They specify the name of the table that they want to summarize and the variables that they're interested in, and that creates the marginal distributions. And then another function, they do export marginal distributions, give a name of a folder, and that exports it out to some CSV files, which I'm going to show you now. So can everyone still see it now that I've switched over to RStudio?
Yeah, it's coming through.
Great. Okay. So first of all, we have a summary, which just gives the number of variables and the name of each variable. For our binary variables, you can see we've got the proportion who've had a stroke, which is about 4%. For categorical variables, it's kind of long format where we've got each value, the variable it comes from, and the number of individuals. For the continuous variables, there's that lookup table I showed you before, but for the actual variables. So see, for example, for age, you can see that age 16 corresponds to minus 3.88. And epsilon there is just the error that was allowed in the Raymer-Douglas-Pucher algorithm for that particular variable. So these are very non-threatening, obviously. You can open up these files, you can see that it's clearly not individual data, which is not always straightforward with synthetic data, and that gets emailed to the user. Okay. So if you're a data user then, you receive the email with the files. You import those into R using import marginal distributions, and then you need to synthesize the data. Now, if you know how to synthesize data, then you don't need to use RESIDE, you can do it yourself. But lots of people, maybe they're not that familiar with it, they just want to see what the data are like, they just want to see if they can run their models. So we've used the Sim Study package because it's well documented, it's quite actively developed, and it's got sampling methods for different data types. And we pretty much wrap that just a single function, synthesize data with imported marginals, and that creates the simulated data. And you can see the first 5 lines here for some simulated data. Sorry, the first 5 and the last 5. So we've got sex, atrial fibrillation at randomization, stroke, yes or no, or so on. By default, it just assumes independence for the first simulation. So I'll show you, here we go, we can then, just like before, we can fit a regression model to the data as exactly the same one as before. Unsurprisingly, the coefficients that you get out are different because you've assumed independence between the variables. But it shows you that you can at least run the model on the simulated data and get a sense of it. However, RESIDE also allows you to synthesize data with correlations between the variables. Now, the correlations have to come from your knowledge or your hypothesis about what the correlations would be. But if you are a researcher, for example, with a hypothesis, then you should hopefully be able to hypothesize the relationship between those variables that you want to find out about to see whether it's worth you getting this data from the safe haven. So we provide a function, export empty correlation matrix, and then that can be opened up in Excel or in, anything you like, and you can re-import it. You can edit the correlation matrix. And yeah, here we go here. So here's doing it in R. We're just assuming a correlation between delay and stroke risk, and then we can synthesize the data again, this time assuming independence for all the other variables and just assuming a correlation between stroke and delay. And this was kind of deliberate to our philosophy. We wanted people to be able to synthesize data quickly and only make it as complicated as they need to make it. So if you, to check that you can fit the models that you want to fit, or to check the data's fit for your purpose, if you need to make lots of assumptions about correlations, that's fine, specify lots of correlations. If you just need to make them about particular variables, you can do that too. So here again, we just run the same function, synthesize data. This time we specify a correlation and we simulate the data. And now we fit the model again, same model, and now if you want to compare the coefficients for the real data, the first simulation assuming independence, and the second simulation assuming a correlation, then now we find that we do find an association between delay and stroke. So, gosh, I think I've been too fast. Anyway, so in summary, here's that same plot I showed earlier. It's really just about, two partners, a safe haven side and a user side to try and facilitate communication of data. We've just got two functions that need to be run on the safe haven side, minimizing the amount of effort for them. They can check the files. And then similarly, if a user just wants to have some data and just wants to see what the data looks like, they can get going with the synthesis on their side. Limitations. So at the moment, the version that's on CRAN is not set up for use with multiple tables, but that's coming very soon. Ryan's about to push that change. We also need to be able to deal with categorical variables with lots of levels. They're very common in routinely collected healthcare data, as you might expect. So things like the World Health Organization ICD-10 or ICD-11, which is coming as hundreds of levels. One way of dealing with that is to have some terminologies that RESIDE will know about, so that you can kind of summarize some of those and populate them on the user side. A more serious problem is categorical variables with 3 or more levels, where you really have a choice of evils. You either have to assume that that variable is independent of the other variables, or you have to assume it's kind of ordered, like a sort of ordered factor, or you can create dummy variables and then make an assumption about the correlation between those dummy variables and other characteristics. But then, unfortunately, in your simulation, you will generate nonsense sometimes, like someone who simultaneously has brown eyes and blue eyes in your simulated data set, which would need a bit of post hoc conversion. as far as we're aware, this is not just a problem to RESIDE, this is a problem that's not been solved yet about synthetic data. And that's the end of my talk. So thanks very much for listening.
Okay, thank you very much, David. I don't see any questions on the chat. I just wondered, is it too early, David, for you to have had any user experience or feedback from this just yet?
Yeah, so we've had the Safe Haven in Glasgow have a play with it, and they found it straightforward to use. It's very fast. It is trying to do something really simple, but I do think that there's a role for it, and I don't know if anybody's ever had any experience in getting synthetic data, even for kind of running kind of HTA models and things like that. But it's incredibly difficult. I mean, if you look at CPRD's website, for example, the Clinical Practice Research Data Link that provides primary care data in England, you're required to sign a full-blown data sharing agreement in order to get crudely synthesized data that doesn't respect relationships between variables. So we're in that space.
Okay. Thank you, David.